Hello, welcome to the second lecture about uncertainty analysis. Let me directly start with the material that we are going to cover. Okay, now in the first lecture, we talked about accuracy and precision and systematic error and random error, the difference between them. Actually, I have not talked about how to use them in practice. This lecture, and it's going to be a little bit of longer one, is going to be a kind of bridge between theory and practice. It's not going to be, again, a total a manual of how to use these methods practically. It's going to be, I'm going to leave that to the third lecture, but I think it carries the most theoretical significance and also practical significance when it comes to determining the sources of error. So I believe this is the most important lecture that you should understand, and maybe in the first iteration there may be some points that you miss. Once you understand the third lecture, which is going to be about measuring uncertainty or computation of uncertainty with propagation of uncertainty with those calculations, you can later come back to this lecture and understand these concepts more thoroughly. Okay, I think I haven't given a definition or the concept of uncertainty yet. So in this lecture, I'm going to try to do so. So let's again start from a more familiar concept, which is measurement versus measurand. And although I haven't given the term measurand in the first lecture, I talked about this concept. We should distinguish between what we measure here, which is an ontic quantity, measurand, which is some real outside objective reality, I may say. All right. And we should distinguish between this concept and measurement. What we observe or what we measure, how we gain information about this outside world. So what we really know is our measurement. It's not measurand. So it's going to be an epistemic quantity. So there's a distinction between those two. From this quantity, we would like to obtain information about the objective reality. So we should realize that the measurement itself is not the outside reality. So if the weight of the object essentially is a measurand, our measurement is actually weight measured, computed, maybe using a theory by an equipment person, all these combinations in a laboratory at a specific time. And one may easily ask here, how are we going to guarantee that the measurement will be a correct reflection of measurand? And this science related with this whole measuring concept is called metrology. And here, for instance, the laboratory balance that we are using, should they be adequately constructed and also correctly calibrated using standards. Here, the calibration concept is very important. From time to time, all laboratories, including our laboratory equipment, are calibrated. Sometimes we calibrate them. But there's a formal institute, for instance, in Turkey, who calibrates, who makes these calibrations. Just to give you an idea about that, let me show you. TÜBİTAK National Metrology Institute, for instance, I am now showing you the internet site. For instance, is especially or specifically related with this issue. For instance, it says the institute aims to ensure reliability of all measurements conducted in Turkey to make provisions for integration of these measurements into the international system to develop. It goes on. Of course, the institute develops and maintains national measurement reference standards and establishes their traceability through SI units, which practically means if you have a laboratory balance, let's say, you would like to make sure that 1 kilogram, when it says 100 kilogram, you really would like to make sure that it is actually 1 kilogram without bias. Of course, there's going to be always experimental random errors, but you would not like any bias stemming from the construction or anything like this, and that is actually the institute which tries to make sure that it is so. But as we are going to see, there's always going to be some bias, almost impossible to reduce to zero. But actually calibration from time to time tries to deal with this issue. Anyway, let me come back to the presentation. So referring to statistics, our measurement is an estimate of our measurement. That's why I put ahead. Think about the population parameters and sample statistics. This left-hand side would be a kind of sample statistic, is going to be an estimator of the population parameter. So just like sample statistics, measurement will change. This is going to be a random variable, right? It's going to change from experiment to experiment, although measurement is the same here. So that's an important point here, which we are going to deal with. And there is another important point I would like to mention here. Please note that all the things that we are going to cover, they do not need to involve a single measurement such as this one. There may be a series of measurements, one after another. There may be computations, and at the end, you are going to determine a quantity. We are talking about actually all the intermediate measurements and also the quantity at the end that we obtain. For instance, we may be interested in the Reynolds number of a fluid flowing in a pipe, and there is no Reynolds number measuring device. We are going to measure the density, diameter, velocity, and viscosity of the fluid inside using different equipment, different procedures. Then we are going to use an equation and come up with a measured and computed Reynolds number. And note that this is going to be a measurement. It's going to be an estimate of measurement. And if you repeat this experiment again under different conditions that I'm going to be talking about, you are probably going to obtain a different measurement value, different computed value for Reynolds number, which means that that Reynolds number, the measured plus computed value here, is going to be an estimate. Here is going to change from experiment to experiment. That's that actually leads to variance and also, of course, bias of measurements and uncertainty. Since this, what we measure and compute, this whole thing, I'm going to simply call it measurement, but there is always theory and computation inside a measurement. Please note that. There is no what we may call naked measurement or sole measurement. There's always some theory and computation there. Anyway, so since any single measurement is an estimate of that outside reality, therefore it's an estimate, therefore it's a random variable. It's going to change from experiment to experiment. Therefore, just reporting a single point estimate is not sufficient. So just saying that we compute or we measure Reynolds number to be equal to a single value is not sufficient. We also report a potential error term or a variance term, which here in measurement theory is called uncertainty related with that measurement. So reporting the point estimate, I'm comparing with statistics. Think about the concept of confidence intervals or confidence bounds. We do not only report a single point estimate, but we also report a confidence bound to give the confidence or uncertainty of our estimates of our measurements. Here is the same thing here. When we measure a quantity, it's not only a single value. The single value is going to be our point estimate of reality of the measurement, but we also need to report uncertainty related with our measurement to give the whole picture. So the single measurement result is not a single number. It is a single number plus some percentage or uncertain or plus minus uncertainty term. This should be our formal approach here. Now, I think one is pretty much justified in asking the question, why does a measurement of a measurand changes? Because measurand is same. We assume that the outside reality, the weight of an object, if we are talking about Earth, of course, is going to be identical at different times. But if you use different balances, different times measure these, the same object, you are with different personnel, you are going to be obtaining different values. So we can summarize the conditions which changes the measurements as time, for instance. When you in short time intervals or in long time intervals, depending how much you how do you define a time interval, the length of a time interval, you are going to see deviations in your measurements. Well, the typical cases in short time intervals, it may be the surrounding conditions like day and night, and in long time intervals, it is usually the equipment with which we use our measurements. Its calibration gets worse and worse, therefore it needs to be calibrated again. So therefore time may be not a direct effect, but other confounding variables which are based on time may affect our measurement. Note that one of the very important sources of measurement differences are instrumental differences. If you use a different laboratory weight, you should probably very easily visualize in your mind that you are going to, maybe slightly, but still you are going to obtain a different result. And that comes, as we are going to see, from the bias of the instrument. So it's going to be instrument to instrument variability. And it's going to be operator to operator, maybe not in terms of weight, but it may be also, if it also includes, for instance, sample preparation. Let's say that in the manual, it says prepare 100 grams of something, right? A very careful experimenter or operator tries to make it very close to 100 by drop maybe, but a less careful one is going to be a little more reluctant to be that much careful about those details, and there may be a higher variance, or depending on the experiment we proceed, it may cause a bias in our results. So it's going to be a higher uncertainty. It's going to be a measurement difference. So this also may depend on the procedure to procedure and also sample to sample. We may prepare a sample, then we are going to prepare another sample, let's say. Then there's going to be, of course, variation due to the amount that we put in our spoon, or we are going to use another, the same chemical, but from another box. There may be a difference between the previous one and the current one that we use. The procedure that we use, for instance, it says wait for about half an hour, it may say. Then somebody waits for 32 minutes, the other one waits 28 minutes. So there may be differences related with that. And maybe one of the most important distinctions, which or the variations come from including all of these laboratory to laboratory variation. Note that there's going to be probably a time difference, personnel difference, procedure difference, operator difference, surrounding conditions difference. So one may visualize all of these in a single diagram, such as this one. Call x-axis as different conditions and y-axis as measurement values. So a single measurement is going to be here, as you can see, right? And if, for instance, you increase the number of measurements here, as we go to the right hand side, the conditions and number of experiments are increased. You may think about in that fashion. So here, let's say that we use the same sample, same operator, but and also same instrument here, right? You just repeat your experiment. You yourself just buy the equipment, and you have the same sample. You take half of the sample or third of the sample, 1/3 of the sample, and you do your experiment. Then you take it again. You do repeat experiment, and you repeat again. So in the end, it's going to be 3 repetitions. But even if you do that all by yourself under the same conditions, it's going to be one by one after another. So let's say that each experiment takes about 1 minute. So the effect of time is also very low, but still there's going to be some differences. So this is the smallest difference probably that you can obtain in your experiments. If you lose some of these conditions, let's say same operator, same instrument, but different samples. Let's say that for each case, you didn't divide your sample into 3 and you put them in your experimental measuring device. You prepared a sample and use it all in your experiment, and you prepared another sample, maybe from another box, whatever. Then you perform the experiment. The variation is going to be higher. And here, this is usually called repeatability. So using different samples, but using the same operator, experimental, on the same experimenting device, when you repeat the experiment, how much the result is going to change is called repeatability. And I'm going to show you an example of that. And let's lose some of the more conditions. This time, you and your friend are exchanging the conducting the experiment on different samples, but the same instrument. So the effect of personnel or the operating person comes into role, you are going to have a higher variance. So the result is going to be in a wider range. If, for instance, we are in the same lab, but we have a number of different measuring devices, a number of different, let's say, laboratory balances to weigh objects for different personnel, different samples, and different measuring devices are used. So there's going to be even a higher variation. And maybe the highest variation is going to be when you conduct these experiments also in totally different labs at totally different times. And this is called reproducibility. And it's going to be probably the highest variance. However, note that these are not very much related with where the true value lies. We hope that the true value lies somewhere here, because the true value is related on the accuracy of these measuring devices. We may easily come up with a scenario that both of these labs, actually all the labs in the whole world, are buying a certain measuring device, but for some reason, this measuring device is calibrated incorrectly. Well, this may seem a very unrealistic scenario, but as far as I know, until the recent 10 years or so, the mass of proton was known to be with an erroneous value about 1.5%, if I recall correctly. So one may liken to that thing there. So from that perspective, it is very possible that if all of the laboratory equipment are not unbiasedly calibrated, then the true value is going to be still outside. But if they are calibrated correctly, probably the true value is going to be somewhere here. I don't know. Maybe it's going to be here. It's going to be maybe a little bit lower, maybe a little bit outside, or pretty much on the center. But I think you get the idea. The important point here is in our laboratories as chemical engineers, we are going to be, I'm going to mention that more in emphasis, we are going to be usually in this part, single measurement, or at most we are going to be using same sample, maybe a couple of samples, but using the same measuring device and usually the same personnel. So we are going to be around here. So just using the information here, can we come up with a, let's say, an uncertainty which corresponds to a kind of confidence interval, which is going to accompany our point estimates, which are going to be our point measurements, so that when you also include that uncertainty interval, we are going to be including the true value. That is the idea. One may easily say that, okay, so since this is the widest range, why should we do this experiment in this fashion? It's bad because here we are going to come up with a small range. Unfortunately, that's not the idea. Even if you conduct the experiment here, a single one, you should come up with uncertainty values such that it's going to almost consider all of these errors. Although if you haven't done these inter-laboratory experiments. So as an example of reproducibility, I would like to show you this screen here. All right, so this is something I was interested in about, let's say, I don't know, maybe 10 years ago. It's something related with, the details are not important. It's about processing oils. So it suggests a procedure which is called ASTM standards, For those who are interested, ASTM International, you may Google it and see what this is. So anyway, we talked about an experimental procedure, and at the end of the experimental procedure, it says about precision and bias. The precision of this test method was blah, blah, blah, and it can be approximated as repeatability is 1.3%. Let's remember what repeatability was. Repeatability, if you conduct the experiment in the same laboratory, using the same measuring device, using the same personnel, but using different samples. So you prepare a sample, you measure it today, you prepare another sample, let's say next day, you measure it the next day. The difference between them is going to be the repeatability. Well, the difference is not the one, if you have, let's say, if you conduct 5 of these, then there's going to be, let's say, repeatability is related with the range or standard deviation of those experiments. I'm going to talk about that later in more detail. And reproducibility, please note that this is much, much higher, but remember that triangular thing here, we are on the pretty much on the right hand side. If somebody else conducts this experiment on a total different sample with total different equipment, blah blah, then the same value can be reproducible up to 7.8%. One may think about the concept loosely in this fashion. And it says there is insufficient interlaboratory test data to establish a statistical statement for bias. Note that even this reproducibility and repeatability is related with precision. Bias is, as I said, is not related with those values, whether in the whole world or in those laboratories, whether the measurements, the measuring devices are accurately calibrated or not is a totally different story. All right, now let me continue here. Can I write it on the page? No, I cannot. All right, so let's continue. Use of reporting uncertainty. Now, this may seem a little bit burden at this point, because once you find a point estimate, a point result, why using this also try to come up with the uncertainty values? Well, there are a couple of reasons. First, I think the most important one, while computing uncertainty here, right? Like a detective in crime scene investigation, one may determine the important sources of error and take corrective actions for successive experiments. What do I mean by that? It's not only coming up with a single value, it is also the procedure during which you do these computations, because once you start coming up with these uncertainty values, you also take regard into these factors, and you can come by also using the values of each of the uncertainty values assigned to these or related to those conditions or these factors. You may easily determine which of these conditions are the most are the most suspicious ones, as the crime scene investigation thing. Who might have detected the crime, which is might have come up, or who might be the reason for the erroneous result. So you may realize that, for instance, there is the most important thing maybe from operator to operator variability, and you may find there is a bias in some of the operators, which means they incorrectly apply the procedure, or they might be doing something different from the operators, from the other operators in a procedure. They, for instance, wait for, I don't know, 35 minutes, while it says wait for half an hour, and that additional 5 minutes is detrimental for your measurement, it may be. So you may find out which of the steps in your experiment might be causing the gross error, or might be the dominant terms or dominant steps which may be causing error. So this is one of the most important aspects of why we do uncertainty analysis. The second one, uncertain values, gives an idea about quality of the experiment. What do I mean by that? Usually at the end of the experiment, we find a value, for instance, a rate constant. you go and check the true value of that rate constant. Actually, there is never going to be a true value, but there are some probably better experiments for that rate constant. So you can you compare it with a benchmark, let's say, a rate constant value. And if the difference between them, the percent error difference between the benchmark value and your point estimate, you find it, and let's say you find an error of 15%. Now, would it mean that there is something wrong in our experiment? Now, if you have done the uncertainty analysis, and if your uncertainty analysis says that there's a 20, let's say, percent of uncertainty in your results, then you can say that under these conditions, this result that I have found is pretty much compatible with the benchmark value that are found in the literature. That uncertainty, which is equal to 20%, may be too high. Then you would maybe like to decrease it by going over the steps one by one and the checking the contribution of each step to the uncertainty, which is actually what I try to suggest in step one. But when you find this result, a 15% of deviation from the benchmark K value and your K value, you do not need to be alarmed if your uncertainty value is, let's say, equal to 20%. On the other hand, if the uncertainty value that you have come up with is 2%, and the deviation of your result from the benchmark value is, let's say, 15%, then there is a bias. It means that there is a systematic error or maybe a random error that you haven't included in your calculations. You should go back and check. There may be a very fundamental error that you haven't considered. And as a third one, this may be more elusive, but also is an important concept. As an experimenter, let's say that you have read the repeatability and reproducibility value. The reproducibility value was 8%. I have just shown for the ASTM standard paper I have shown you, whatever that experiment was. And that 8% means that in a different laboratory, when you conduct the same experiment, you should not expect a better result than a deviation of 8%. Very informally, it corresponds something like this. Let's say that you would like to measure a quantity. You would like that quantity to be able to sell that material, to be the product. It should be equal to 95 some unit, whatever. You measure it, and the result comes out to be 98, let's say. And you send it to the customer, and the customer measures it, and he or she comes up with the result of 93. Okay, 98, 93, and the value that you would like is 95. In this case, it is not very much realistic to try to reduce the error here. Let's say interfere with your production, because practically 98 and 93 is within the reproducibility limits, because these analyses are conducted at different times for different samples from the same, of course, batch from your production. So they are comparable. It is very likely that they come from the same distribution. So it is not, it's a little bit of futile to try to drop this discrepancy and compare it with 95%. One may liken it to a hypothesis test. Here, the difference between the laboratories is not significant compared to the reproducibility value. So since the reproducibility value is 8%, which is maybe a little high or relatively high, any value smaller than that, when you obtain, it is not very realistic to try to reduce that value. I hope the idea is clear. So it gives you an idea about the sensitivity of also your measurement results. So how much of a deviation is significant? It also gives you that idea. As I said, this also looks like a hypothesis test. Only a deviation exceeding the reproducibility value or uncertainty. They're not the same thing, by the way, but just to give you an idea, overall idea about what's going on. So just deviations exceeding uncertainty should alarm you that there is something else going on which you haven't included in your analysis. Now, when it comes to the factors that contribute to that cause uncertainty, we may divide them into three different headings or items. The first one is test conditions. It's related with the testing equipment and the procedure itself. So the very important point here is the calibration of the measurement devices. While these should have been previously calibrated, correctly calibrated, such that there is no bias in the measurements. So this calibration is the calibrations. Of course, you are not going to be conducting the calibration as far as I know, but from time to time, the measuring devices should be calibrated. You should know that. And this is very much related with the concept of slow drips in calibration. Well, almost all sensors, all measuring equipment, and also generally sensors in chemical and process industries, they lose their accuracy in time. This is related quite possibly with the concept of entropy, its friction, or similar factors that cause their lose accuracy. Therefore, there should be recalibrated periodically. And these are called slow drips, which is a very important problem. And also ambiguity in experimental procedure is another problem or another cause of uncertainty. As I said previously, if it says wait for a half an hour, that doesn't seem very precise, one may say. So one may tend to maybe wait for 31, 32 minutes or something like this, or 28, 29 minutes. So if the results are pretty much dependent on that waiting times, those kind of ambiguities in experimental procedure are one of the important factors contributing to uncertainty. Now, test environment are related with the effects surrounding the test equipment, I may say. What do I mean by that? For instance, usually in our experiments, since we are chemical engineers, we are going to be dealing with gas and liquid flows, and most of our experiments will be liquid flow. And you are going to realize that, perhaps you already know that, there's going to be special and especially temporal variations of flow. You would think that it is 1.3 liters per second. It is what the indicator or the measuring device says or reads when you look at it. But if you look 1 second later, it's going to be, you are going to see that it's going to be deviating a little bit more or less. So fluctuations are usually going to change in time direction. And it's not going to be a very smooth flow for most of the times. And that's more problematic because there's going to be special variations of flow, which is much more difficult to determine or to see. And sensor location is an important aspect here. Let's say that you have a poor stirring here, right? And your sensor is located in this tank, and you are going to conduct concentration measurements here. And if the stirring is not what we call well-stirred tank, usually in computation analysis, we say that let's assume that we have a well-stirred tank, but is it really well-stirred? Which means that there should be uniform concentration here. But is the reality so? Well, that's questionable. So the location of the sensor is going to change is going to have an effect on the result. And here, for instance, there's going to be probably a bias depending on the sensor location. Or if we have a flow here and we take a flow measurement here again, if the flow is highly turbulent here, then the flow measurement may not be precise, or it may be pretty much fluctuating. So it's going to be a huge contribution to uncertainty. Similarly, poor stirring is also, I have tried to combine it with sensor location, and there might be impurities in our flows, in our water flows, liquid flows, or in our chemicals. We usually say that, okay, let this be the concentration. So we take a certain amount of mass of a chemical, let's say using a spoon. But the problem is there no impurity in that? And we mix it with water, right? That's great. But what about the impurities in water? Okay, we use distilled water, but there may be still impurities or other things that we haven't considered. So these are environmental problems. Another important thing, and that's an interesting thing that in your experiments maybe you would like to investigate, is the so-called wall effect. Please Google it, with wall effect with uncertainty. It's an interesting concept. It simply says that, for instance, when you would like to reach terminal velocity is simply if you drop, let's say, a ball, and this is, let's say, the surface of the earth from a very high distance, then at some point it's going to reach terminal velocity. On the other hand, when you conduct similar experiment, right, in a fluid, let's say with metal balls, the idea is still the same. This experiment will not give an identical result compared to conducting this experiment in an ocean, because in the ocean there's not going to be a wall effect. It's going to be very deep, so the terminal velocity is going to reach somewhere here. There's a very long distance. On the other hand, here, when the terminal velocity is going to reach somewhere here, let's say, it's going to be very close to this floor here, and that wall effect, due to the displacement of water and things like that, let me not give you any spoilers about that, this is going to be affecting our results. So similar other, there may be test conditions, is going to be affecting the uncertain or giving uncertainty values. Now there is going to be another source of uncertainty that I'm going to be covering probably 2 or 3 lectures later. Is in more detail, is going to be uncertainty due to models. This may be usually related with assumptions. Very simply, for the timing, I'm going to be talking more about that also in this lecture. For instance, you may assume ideal gas, but the conditions of ideal gas does not hold for the current conditions. So it's a poor assumption. So that may be a cause for bias, for instance, which is an uncertainty. And model process mismatch is the model that you use is inappropriate for the process at hand. Very simply, your results, for instance, look like a quadratic curve, but you fit a straight line. So there would be a bias term stemming from that model process mismatch. And there are other reasons for uncertainties. Even you have a linear fit with a seemingly linear observations. Due to the random error term, there's going to be an uncertainty in parameter estimations, and I'm going to come to that. So there, basically, you can put them into 3 classes. There may be more, but you may start thinking about those and try to come up with, just like a crime scene investigation, which of these factors contribute how much to the uncertainty and which of them seem to be dominant. That may be the usual approach that you use. So there are actually 2 types of uncertainty evaluations, what we call type A and type B. They are very simple. Type A is related with repetition of experiment. We're going to see that what repetition of experiment correspond to, but if you repeat your experiment and come up with some uncertainty values, these are called type A type of uncertainty evaluation. Type B uncertainty evaluation has got nothing to do with the repetition of the experiment. So even if you do not repeat your experiment, so you may think about like this: there are some certain uncertainty values which can only be obtained by repetition of experiments. These are called type A evaluations, right? But there are also some the so-called type B evaluations of uncertainty. These have got nothing to do with experimental repetitions, right? Even if you experiment, if you repeat the experiment, it's going to give you no idea about these type B uncertainty values or evaluations. These are going to be obtained by the so-called resolution of the equipment, which we are going to cover, manufacturer specifications, again, we are going to cover, or in some cases, it may be intelligent guesses depending on experience or maybe from literature, other sources. So they are going to be, even if you, I repeat again, even if you conduct a single experiment, still you are going to be able to come up with these type B evaluations. But if you conduct a single experiment, type EA evaluations would be missing. But if you conduct repeatedly a number of experiments and do an uncertain evaluation only based on these, usually they are going to cover type A, right? And type B would be missing. And usually it's not always the same. It depends on your sampling, but usually it's going to miss the whole picture. So a complete uncertainty evaluation usually will consist of these two evaluations. And I'll come to the what these correspond to more detailed meaning now. So what I'm doing right now is I'm going to try to dissect in a way or try to explain contribution of various elemental, systematic and random errors to uncertainty. So it's not going to be a complete treatment. The complete treatment is impossible actually due to the limited time and also the content of the course. This is not a metrology department or course, but it should give you enough insight and information, adequate information to put on your knowledge about statistics, and it should be useful for your laboratory experiments, and I hope it will be. So here we assume that experiments are conducted under typical university undergraduate laboratory conditions. What do I mean by that? For instance, let me talk about the extreme case. We are not going to be talking about reproducibility. What do I mean by that? Let's remember reproducibility is two different laboratories. It's going to be usually a single laboratory because we are in university, and it's going to be in a single laboratory. There's going to be a single equipment to measure. Usually there's going to be a single flow rate measurement. For instance, we are going to be using that single flow rate to measure the flow rate at different times maybe. And there's going to be a small number of repeated experiments. That small corresponds to something like 3 to 5 at most. And in some cases, it's going to be a single experiment, but not much more than. We are not going to have a repetition of 100 experiments. It's not a very realistic experiment expectation. And we are going to be using the same instrument. Usually the same operator is going to be using, because students are usually divided into a number of subgroups when they conduct the experiment. One person writes the result, another one looks at the flow meter, and the other one uses the watch or something like this. They do not change those people using the experiment, but sometimes maybe. So we can say that same or different operators and same and or different samples. It depends again on the experiment. If you need to prepare, if you need to do a repetition of the experiment, usually the same person takes a spoon and prepares another sample, usually from the same box of that chemical. But sometimes it may be from another container also. So also I put here same or different samples, I may say. So the change would be usually same different operators, same different samples, but usually even they are the same. The most important distinction is going to be a repetition of the experiment in a short time interval. So we are going to concentrate on for the specific scenario, and for this specific scenario, we are going to be talking about some elemental sources of systematic and random error. First, I start with as you can see, it is 0. It's not 1, because this is not an systematic. This is not an uncertain term that we are going to be using. but this is a problem that we need to first handle. This is called consistent. There should be a T here, consistent bias. And this should be handled prior to uncertainty analysis. Now, this means significant and consistent bias in measuring device operator experimental procedures. And these should be corrected. Very simple example. Let's say that you are going to measure the water level in a graduate cylinder. This is the meniscus of the graduate cylinder. And one of your friends starts measuring this. And he or she says that, oh, we were measuring the highest, we were reporting the highest values touched here on the walls, right? He says. And the other students correct him or her. No, it is actually the lowest level that you should report. If, for instance, up to that point, all the values were reported using these values, then practically what you should do is you should find an estimate of the difference between those two and correct all the values up to the sampling point here. So basically, if we use a correction, this is defined as the measurement average minus real value. Then for future measurements, we use the measurement minus correction. Well, it looks complicated. It's very simple, actually. What it means is this, for instance, and this is not that it's going to be a type B assessment, because this has got nothing to do with the repetition of the experiment. Here, what I'm going to show you. Here, let's say we have a balance, but for some reason, we are not sure whether it shows unbiased measurements of weights. So let's say we have some standard weights here. We know that this is 100 grams. We know that this is 250 grams, 500 and 1,000 grams with some significant periods. We weigh them, and these are the results. The 100 gram is measured to be equal to 98. This is 250, 500, and this is 1,000. So the error here is equal to minus 2 grams, minus 1, minus 2, and minus 1 gram. So what I do is I take the measurement value, I subtract it with the true value. True value here is 100, this is 250, and this is 1,000 here. And these are the error values that I obtain. If I show these error values with respect to the true values, this is the diagram that I obtain. What this diagram shows is the bias values here do not change with respect to mass values. So whatever the mass value, there seems to be a constant bias here. You may say, what else could have come out? Okay, this could have come out, for instance, easily. Which would correspond to, let's say this is 98, this is 445, this is 480, and this is 950. As the mass is, as more mass is put on the balance, then the error would have become larger. That could have been the case. In this case, I would not be able to use this method here. That's a little bit more difficult thing. You are going to use linear regression, but we are not going to be dealing with this case. Anyway, error is constant with respect to mass. Now, once you make sure that this is the case, then you find the correction here. Correction is going to be the measurement minus real value average. So basically, it is those error values average. Minus 2, minus 1, minus 2, minus 1 over 4. It is minus 1.5 grams. So let's say that we cannot calibrate this measuring device. We don't know how to do it. And we are going to start our experiment. We measure something, our sample, and that sample comes out to be 342 grams. In this case, the corrected measurement would be 300. Well, actually, I wrote it incorrectly here. It's listed at 324. This should have been. So it's going to be 324 minus 1.5. So basically, you add 1.5 grams here, and 325.5 grams should be the corrected value. And this is called bias correction here. And this is how you can apply. Well, a similar situation, actually, scenario has occurred in our laboratories. You are going to see, we are going to have in one of our experiments, we are going to have 3 connected stirred tanks connected in series, and we measure concentrations here using conductometers, conductometer 1, 2, and 3. And we were suspicious that there might be something wrong with the calibration of these conductometers. So, and we have realized that, and since actually these 3 tanks, actually note that they are going to be, during the experiment, they are going to show different concentrations. So it is pretty much realistic to obtain different values from the conductometers. But for some reason, we felt suspicious. So therefore, in the same concentrated container, we put all these, well, one by one, we measure the concentration using each of these conductometers. And we realized that conductometer 1 and 3 gave identical results, almost identical results, whereas the conductometer 2 gave different results. So these are hypothetical values. So let's say we prepare a solution here. Conductometer 1 and 3 give these results. Conductometer 2 gives this result. And we slightly add more of that solute. We increase the concentration of solution. So these are the results. As you can see, there is a little deviation between them, but this is like a repetition of the experiment. So it should be, but there's a larger deviation to the second conductometer, and it goes like this. So the very basic analysis that you should do is we come up with an average of C1 and C3 as these values, 2 and 2, 2.4, 2.45, and we subtract the C2 values from these average values, and we find the error terms. Note that there is an important distinction between this experiment here and this correction here and this correction here. That was a type B assessment because we had these external weight values which we know to be true. Here, for this case, indeed, we do not know whether C1 and C3 is true. Actually, we don't care about that here. As long as they show the same value for the same solution, that's okay. So which one? Maybe C1 and C2 are both bad or not well calibrated. C2 is the correct one. But here they do not give the same answer. So we concentrate on the majority as the appropriate one, and we adjust the other one using those two. But to be frank, that's not necessarily a realistic assumption because actually none of these were calibrated for a long time. And since C1 and C3 show very close results, it probably means that, of course, it should be again checked, but there's something wrong with C2. Anyway, again, what we do here is we plot these error values with respect to C1 plus C2 over 2. Here, this corresponds to somewhat like true values, but it's not actually. That's why this is a type A assessment. Note that the whole assessment is done within the experiment, the repetition of the experiments. So when we take these values, show these values, we see that bias is independent of C, right? There seems to be just a small fluctuation, so it seems to be constant with respect to concentration values. So we simply take the mean value. I repeat that again. If this were not the case, finding the mean value and using would be inappropriate from a statistical point of view. So we have a bias of minus 0.25 between the second and the first third combination of conductometers. So if in the future we obtain a value of 0.8 measure, then we are going to add this value here because it's minus. If you go back to these equations, right, measure these equations, it's going to very easily show you that this is the case, why we subtracted. Then the actual value that we are going to report is going to be 1.08 or 1.1, depending on the number of significant figures that you would like to use as the conductometer reading from the second tank. Okay, but as I said, recalibration is of course a better strategy, but during the experiments, if you do not know how to recalibrate and if you don't have the equipment or knowledge to calibrate, that bias correction is an important concept, and this is prior to uncertainty. This is not involved in uncertainty analysis. Now let's start with how to deal with uncertainty or the factors related with uncertainty. The first and the most obvious uncertainty comes from finite resolution of measuring devices. And this is a type B evaluation totally. Let's call this delta to be resolution of any equipment. What do I mean by resolution? Let's say that you have a laboratory balance here, you weigh something and it shows with 1.8 grams, it says. So one decimal figure here after one figure after the decimal point in terms of grams. Now note that if you call it X to be measurement here, the measurand, call it X something else, practically is going to be between 1.75 and 1.85 grams. Actually, it's not going to include 1.85, it's going to include 1.75, but this rounding off is that convention, it's no big deal. But anyway, think about, even if this is essential, this measurement is 1.76 grams, still it's going to be shown as 1.8 gram. So there is going to be a 0.1 gram of resolution here. So how are we going to change this to uncertainty? Now here, two distribution models are usually used for reporting or assessing uncertainty. This part seems a little bit theoretical at first, but it's going to be very practical. It's more related to curious minds. One assumption or one model is uniform distribution. And for such machines, this is the one I prefer to use. What do I mean by such machines? Here you got no idea about the next digit. It may be 1, it may be 4, it may be 78, it may be anything. So it may be any value between 1.75 and 1.85, excluding 1.85, with equal probability corresponds to uniform distribution. Here this is going to be actually equal to, no, it's not 0.1, since this is equal, the area should be equal to 1. Therefore, I think this should be, let me put in comment, this should be equal to, I can write, yeah, 10, because when we, or yeah, 0.1 times 10 is going to be, area is going to be equal to 1. Let's keep the statistical statistic rigorous as much as we can. Okay, variance of a continuous uniform distributed variable is b minus a square over 12. B and a here correspond to upper and lower values. Therefore, it is basically range square over 12, and range is what we called here as resolution. Therefore, variance is actually equal to resolution square over 12. So here, this is how we deal with the whole thing. This variance is going to be the square of bias here. So we are going to call it bias due to resolution square is actually equal to the variance here of this distribution. Now, by the way, different sources from the internet, from different books, they may use slightly different definitions here. Some of them use confidence intervals for bias or include confidence intervals. They lead to the same conclusion, but the intermediate steps may vary. But this is actually a proper way of doing that. Other methods are also proper, I may say, but this is at least a consistent method. Anyway, so I take the bias term to be equal to the bias square term to be equal to the variance term. So they are interchangeable. So therefore, when you take the square root here, it's going to be equal to this resolution divided by 2 over square root of, actually this is equal to, very simply, this over square root of 12. And if you write it as 2 times square root of 3, and I put 2 here, therefore I obtain this expression, very simply. Well, one may say, why do I do that? Because it has a meaning here. This resolution over 2 is the half width, which is here 0.5. So therefore 0.5 over square root of 3 is the bias term. All right. Now there is another assumption here. If you assume this to be normal distributed, which means that the reading that you obtain from this measuring device is, let's say it's 1.8. So you are going to assume that it is 1.80 here and it dies out here at 175 and 185. Now, note that Gaussian distribution never dies. It goes to the minus infinity and plus infinity, but practically where this touches here x-axis, this left hand and the right hand is about 3 sigma, minus and plus 3 sigma. So this whole width is going to be practically equal to 6 sigma. Therefore, we can easily say that 6 sigma square is going to be equal to this width is going to be equal to range. I'm very sorry. 6 sigma is going to be equal to range. So sigma is going to be equal to range over 6. So when you take the square here on both sides, it's going to be resolution over 36 here. Now note that here bias is going to be the square root of this term. Very simple arithmetic. It's going to be equal to the half width resolution over 2 over 3. So compared to this 3, we divide this by another square root of 3 here. So here bias and uncertainty is going to be smaller. The idea is very simple because here uniform distribution assumes that it may be any value in between, right? Whereas this assumes that it is likely to be more in the middle. That's why my personal choice is to use this one for these systems where the least significant, for the least significant, or the digit after the least significant figure is totally unknown. I prefer to use this one. It has a slightly larger bias by a square root of 3, but I prefer to use that one. Anyway, for this specific example, let's continue with also by using these two methods. For uniform distribution, the half width is equal to 0.05. Of course, for the other one is also 0.05. You divide by square root of 3, you obtain 0.025, which is equal to 0.03 grams. Now, at this point, actually, I still don't want to show you the uncertainty calculation or how this is reflected in uncertainty, but just to give you an idea for this specific example, I'm showing this. Because in real life, we are never going to be using just a simple weight measurement. We are going to be combining different measurements also, so it's going to be more complicated. But let's say that a very simple uncertain measurement is going to be like this. In this case, uncertainty, the total uncertainty, I may say, is going to be equal to some constant times bias. Later, I'm going to show a more rigorous definition of that or discussion of this, but for the time being, just take it as it is. This bias is going to be multiplied by k, and this k is usually taken to be 2. And where does that come from? For normal distribution, if you recall, 2 standard deviations minus plus correspond to a z value of 1.96. I'm very sorry. Actually, it should be like this. If you would like to cover 95% confidence interval, then the corresponding z value is going to be equal to 1.95, and that 1.95 is almost equal to 2. That's what that 2 is equal to, actually standardized normal distribution value such that the confidence interval is 95. Therefore, we multiply the 0.029 by 2, and the result is 0.058. We rounded off to 0.05 because we don't want too many significant figures here. So we show the result in this fashion. It's always better to put another 0 here to keep the significant figure convention. So the actual value is going to be, this is our point estimate. The actual value is going to be plus minus 0.08. Well, there's a problem with this result. I'm going to come in a minute. And usually, this is not how, well, this is one way of showing your result, but usually we like to show it in this way. What do I mean by that? we find the percent uncertainty, because when you show it with 1.8 grams and 0.08 plus minus grams, we can't really get an idea about the magnitude of this uncertainty. One way to understand, to feel the magnitude of the uncertainty, is to divide this uncertainty value by the measured value and multiply it by 100. And when you do that, we find the percent uncertainty, which is equal to 3.2 uncertainty percent. I'm sorry. And this is how we report it. Our point estimate, or our measured value, is 1.8 with a plus minus 3.2 percent uncertainty of grams. Now, this gives you a better idea about how much confidence you are going to put in your measured value. And if you do the same calculation, this time for normal distribution, since for normal distribution, bias term was smaller by a square root of 3 factor, so the result bias comes out to be equal 0.02 and 0.017 to be exact, but I reported with that many significant figures. But intermediate calculations, I use this formulation. And I have another 0 here, and as you can see, it's a smaller number compared to this one. It should be by a square root of 3, but due to rounding off, there may be some differences. And this is 1.8, again the same value, but plus minus 1.9%. As I said, I would have preferred to use this one here. Now, the problem with this specific example is, instead of all these calculations, just by looking at this example, we should have realized that indeed the uncertainty is equal to 0.05 grams, just by looking at this result, right? This value here, the measurand, is between 175 and 185, and if this value is 1.8, therefore it means that the real value is between 175 and 185. So actually this should be the correct answer. Indeed it is for this specific case. So you may say, why do we have 0.06 here? Because once we conduct repetition of those experiments and also other materials, so there are more terms to be included in the uncertainty analysis, this method, this whole steps, due to central limit theorem, because it includes many uncertainties from different sources, they tend to be a more statistically correct result. So for this very specific example, it doesn't matter which one you use, but just without doing any analysis of all these stuff, I could have easily come up with this result, which is the correct one. But if, as I said, when you come up with other measurements and when you try to combine them, this method fails. This method, so which is basically finding the variance using uniform distribution, then equating the square root of variance, which is standard deviation, to bias, and then multiplying the bias by 2 to find uncertainty gives a better result. Okay, so let's talk about another case which you are going to see in your laboratory, which we have seen in the laboratories previously, usually reading a volume from a graduated cylinder. Let's say that you have a meniscus like that, and your whatever liquid level is between 17 and 16 milliliters, and there is no other, let's say that those ticks here, mini ticks here. So the smallest tick size is 1 milliliter. So what we usually do is, using our intelligent guesses where this meniscus lies, we come up with a value of, let's say, we do not usually say 16 or 17 exactly, but it's in somewhere between, and we do not usually say 16.5. Using our heuristics, we come up with a reasonable value. But note that this is indeed an estimation, a kind of intelligent guess. So basically, there is an uncertainty related with that. So what we do here is very similar. Now, what I did here is I directly use, I don't need to go over these again and again. If I assume uniform distribution, then I'm going to be using this equation. Resolution divided by 2, which is half width over square root of 3. This is resolution over 2 divided by 3. Now, for this specific case, when it comes to graduated cylinder, since indeed we have an idea about where this point lies between 16 and 17, I prefer to use a Gaussian distribution, because this point here, my best estimate, is more likely compared to those extreme values. Therefore, Gaussian distribution seems more appropriate to me. Compare it with this case. For this case, since we do not see what's going on in this second digit after the decimal point, it is, from my point of view, better to use uniform distribution. So what I directly do is I divide this resolution by 6 and find the bias term. So it's going to be 0.017 milligrams, and I multiply it by 2.34 milligrams here. Therefore, the result is reported in this fashion. 16.4 plus minus 0.34. There are too many significant figures here, so I report it that way. I again find the percent uncertainty 2.5. Now, please see how this is gives more intuition about the whole thing. 16.4 milliliters and 2.1% error possible, or a bit uncertain, with that much of uncertainty here. So this is when you include the resolution of a measuring device, and you always have to include the resolution of measuring device, because they always have resolutions. When you use a stopwatch, there is a resolution of that, for seconds or milliseconds, whatever, for volume, for length, all of that.